My name is Timothy Winey. I've been working on some very basic research, hence the name, involving water and other liquids. So I do need to move quickly because there is a wide range of strange and interesting effects here. So I got thinking about boundary layers, and I wanted to do a simple experiment to explore the boundary layer between water and something that repels water in a dynamical system. And so I went to my local shop and bought 2 lava lamps. I figured wax and water would be a good interface. And you will see in the video here that the lamp on the right does not behave normally. I thought it might have been faulty. I switched the bottles to each other's lamps. Didn't make any difference. Bought 2 more lamps. Same effect, 2 more lamps. The wife said that's enough. And so here we go. But first I'd like to just read this quick quote. I think this is apropos to sort of prepare you for the strangeness to come. Faraday says, quoting William Crookes, "Before we proceed to consider any question involving physical principles, we should set out with clear ideas of the naturally possible and impossible. But this appears like reasoning in a circle. We are to investigate nothing till we know it to be possible, whilst we cannot say what is impossible outside pure mathematics till we know everything." So I find that quite stimulating. And so Crookes goes on to say, in the present case, I prefer to enter upon the inquiry with no preconceived notions whatever as to what can or cannot be, but with all my senses alert and ready to convey information to the brain, believing, as I do, that we have by no means exhausted all human knowledge or fathomed the depths of all the physical forces, and remembering that the great philosopher already quoted, namely Faraday, in reference to some speculations on the gravitating force, nothing is too wonderful to be true if it be consistent with the laws of nature. And in such things as these, experiment is the best test of such consistency. So here are some very unusual experiments that I hope will shed some light on boundary layers and other effects. So this is obviously sped up for brevity, but the lamp on the left will begin convecting, and the lamp on the right will take on a stable shape and hold that for some considerable time. So this is not normal. If I bought a lava lamp that did that, I would certainly return it for a refund. So I thought there had to be something wrong with these lamps, so I bought 2 more. And here we go again. This is not trick photography. This film has not been reversed. This is real time, running side by side. 2 novelty lava lamps. Later on, we'll talk about fuel treatments and a change in the freezing temperature of fuel, which may provide some clue as to what's going on here. But these persist for quite extended periods of time. This is sped up several times, obviously. And obviously the lamp on the right, you expect it to pinch off once it reaches a certain waistline, and it doesn't until now. So at any rate, so this is an oil and water mixture. I just took equal amounts of oil and water, put in denture cleansing tablets. The place I buy my denture cleansing tablets is beginning to look at me a bit strangely. They seem to buy a lot of these. And my father, being a retired dentist, I always try to take good care of my teeth, so it's a bit of a mismatch. But so here's an oil and water mixture. We just mix up oil and water, agitate it with denture cleansing tablets, and let it sit overnight. And as you can see on the left, you have a more clearly defined boundary layer, and it's much greater on the left. The left is the structured sample. So we then stir these samples, mix them nice and thoroughly, and okay, so you think, here we go. And what you end up with is a very rapid return of this boundary layer on the left. I've repeated these experiments endlessly, and there's never been an exception. In this experiment, equal amounts of granulated charcoal, I just grabbed ingredients from the kitchen, rice, oil, water, iodine, denture cleansing tablets, and baking powder were added to 2 glasses, left structured, right non-structured, stirred simultaneously, and then left overnight. I've experimented extensively with granulated charcoal and charcoal powder just to increase surface area to see if we could tease out any charge effects. And as you can see on the right sample, the charcoal fell to the bottom, most of it, and on the left, it's inverted. This is a similar experiment using rice, oil, and water, and again, denture cleansing tablets. This is very peculiar. I repeated this many times because I couldn't understand how it could be so different, but as you can see on the left, the boundary layer is very clearly defined, and you can actually see through the glass. And there are many examples of these almost perfect looking layers that form different mixtures. We'll look at some of those a little bit later. I must have bought $200 worth of Mentos candies and did untold experiments with these fizzy drinks, as we say in England, and they are always more energetic. So this is just 2 bottles of Diet Pepsi, I think, and unscrewed the caps and dropped in the candies. And as you can see, the left structured sample displaced much more fluid. This is a live video showing just Diet 7-Up poured into 2 glasses, and it's the same experiment where we just let it speak for itself. I wanted to show this video to show that they were poured similarly and that one wasn't heated up and didn't fizz over. So just to show that very simple experiments that I've replicated endlessly. And we did this because we treated fizzy drinks and they tasted more effervescent in the mouth. They were much fizzier in the mouth. I thought, well, there must be something physiochemically going on here. So they're always more energetic. So not only does it rise up faster, but it wins the race back to the bottom also, which is odd. So the whole thing is just simply going faster. This is I've done sort of modified iodine clock tests where we just mix iodine with different liquids. Again, agitated with denture cleansing tablets. So this is just water and iodine in 2 beer glasses. You can see just faintly at the bottom the little denture cleansing tablets. This is sped up, I think, 64 times. So I'm sure the chemists among you know about iodine clock tests. This is just such a discrepancy in the reaction rate. It's really absurd. Now this is very interesting. These were tests done using a device called the Z-Nose, which is a high-speed gas chromatograph, and it's basically being used to smell all sorts of substances. It's the only device of its kind that's approved by both the FDA for food spoilage and other applications, and the Drug Enforcement Agency. So if this device thinks it smells heroin in your luggage, you're done. It's considered like a guilty plea. So if you look here, I should explain how this works. I had a professor at a university in England do this for me. We spent all day together. And basically he said, I'm going to show you how this works. So we sniffed, I think we started with gin. So we sniffed some gin. Okay, so it heats up the sample, and then it bombards a crystal sensor, and then it gives off the spectra. So the chromatograph can guess what it thinks this is, what it thinks that is, whether it's carbon or what have you. So, but that's not important. What's important is if you clean the sensor and repeat this test, what you end up with, if the machine is calibrated correctly, what you end up with is a perfect tracing. So you'll see a blue line, and then he'll repeat the test, and you'll see a red line perfectly tracing the blue line. So that means it's working. It's measuring the same thing twice. Well, this is This is a sample of gin from the same bottle. The blue was the untreated gin, and the red is the structured. Now this gin was treated and left alone for 1 year before this test. So this structuring effect is remarkably stable. And it tastes much tastier. I'm not a drinker, but it's much less volatile. It doesn't burn your tongue. This is very exciting. We're working with stevia, which is a safe natural sweetener derived from a leaf that is reportedly 250 to 300 times sweeter than sugar. In very extensive double-blind taste testing, we have been able to fool the overwhelming majority of subjects into thinking that stevia is actually sugar, table sugar. So it's a calorie-free sugar substitute that tastes exactly like sugar. Now, with normal stevia, you can only add a percentage, after which point it becomes very distinctive. It gives a very distinct licorice, metallic, bitter aftertaste. So there's a limit to how much stevia you can sweeten substances with. Until now, we just keep adding more stevia and it just gets sweeter. So the blue is obviously the control, and the red is, and here you have a higher peak with the red, but in other places it dips below the blue. So it's not always predictable what it's going to do. So we're very excited about the work with stevia because obviously sugar is a big problem. This is wine from the same bottle. This is a Chilean terrible red wine. This wine was rated stinky armpits by a group of wine masters, and they actually said they would pay nothing for this wine. It was the only wine that I could find that they rated at 0. And I went to this very group of wine masters and presented this wine to them. They said, "Oh, this is tasty. We drink this. Where'd you get this?" I said, "Well, last week you rated it a 0. Awkward silence. And so, as you can see, there's huge spectrographic difference here from this wine. Now, if we look at this professor, apparently has colleagues that are wine aficionados, so they did lots of testing on wine after hours at the university with this device. And they tested 2 different varieties of wine. If you look here, this Cabernet and Merlot, they're as if not, well, you could argue that this is as if not more different spectrographically than 2 different varieties of wine. So here we have wine from the same bottle, here we have 2 completely different varieties of wine. I just decided to spit into some ethanol to see what would happen, and that's what that looks like. And then I decided to structure some ethanol and spit again, and that's what that looks like. So just a random test just to see how spit would behave in ethanol. I bought some ethanol for some combustion tests. So this is a hydrophilic polymer test. I repeated this test many times. I couldn't believe this result. This is just a tall, skinny glass cylinder, and I pour just a little shot glass of this novelty snow. They sell it to kids to simulate snow. It's a hydrophilic polymer. And bulk water, it takes predictably 6.5 seconds to reach the bottom of the glass, and most importantly, if you look toward the bottom, it'll fan out and form a telltale mushroom shape and actually touch the sides before it hits the bottom. So it's a very predictable spread just due to the mechanics of how these polymers absorb water. And then in the second, it hurls what looks like a snowball to the bottom of the glass and does not fan out as expected. So yeah, let's show that again, because that's concentrate at the end of the cycle here where you see the spread. So it actually reached the width of the glass.
When you say structure, how do you structure it?
Yeah, that's a loaded question. Unwitting. So I'll talk about that. I think I'll just try to follow it. Okay. Okay. So These are polymer beads. These are what we call water beads. People used to put them in vases. I don't think you see that much anymore, but these are just microphilic beads. They start out very tiny, the size of a BB. You can put them in water. And this is the same snow that I used in the drop test. I repeated this test many times. I couldn't believe it. We basically just add the same ingredients, same amount, shake up the bottle, leave it overnight. And this is the, we can call it exclusion zone. But importantly, there's always some snow at the bottom of the structure and none on the right. There's a very defined boundary there, and of course the distance is much greater. So this will take a little explaining. These are polymer beads, but I'm showing the film in reverse. So what you're looking at is two bowls full of inflated or saturated beads, and then the film will run in reverse, and you'll see little what look like BBs emerge, and that's the small, that's the dry bead. And if I can, okay, I can't stop this. That's what I want to be able to do. Can I stop this? Can I pause this? No. I don't know if I can pause this or not. So I'll just talk you through it. Okay. Okay, so you'll see, look on the right, you'll see the beads emerge first, and this is the non-structured. So you'll see already lots of little speckles. Then on the left, and then it reverses again. So if you look at it both directions, inflating, deflating, the right absorbs more slowly than the left. So that's the important takeaway here. The structured water is taken up more quickly in these hydrophilic beads. This is another test using clear beads and red beads. So again, on the left here, you'll see an inflation or absorption. It's quicker. On the right, there's still a water line on the right. Here it goes. And then as it reverses, you'll see the water line here forming much sooner than this. So already now, right about now, you're seeing the water line. These are very, very repeatable, very predictable, always without fail, quicker absorption. Now, don't ask me what made me think of this. I got little wooden rings, curtain rod rings, and put them in the center of a bowl, put the polymer beads in the rings so they wouldn't spread out, and let them take up wine or the water from wine. And well, that doesn't look that terribly exciting, but if you look carefully here, what do we see? We see this super clean line once again. This is raggedy over here. And blown up, you see this absolutely regular boundary layer, and here it's much more erratic. Here, again, more snow, more beads. I did this just to test evaporation because we're working now with plants. We think that treating vegetables or the water that is used to grow the vegetables, we believe they will give off water more slowly and last longer on the shelf and be easier to transport and taste better, all sorts of things. So I just added equal amounts of water to these two glasses and just photographed it over a period of time. This is maybe over a 24-hour period. And if you look on the right, this is, I didn't weigh these, but this has clearly lost more water. This is a counterintuitive result. This is a colloid, just milk, 4% milk. And I just threw equal amounts of beads into these. And as you can see, the non-structured milk gave up more water. The structured milk didn't want to do it. And so we empty out the excess milk, and we find a big weight difference here. Obviously, there was a lot more milk left here to pour off. These are just 2 sweet peppers split in half and trimmed to weigh exactly 36.4 grams. And here's a little chart over, I think, I don't know, 12-hour or 24-hour period.
And we see that the structured pepper, not the water to grow the pepper, but the pepper itself, gives up less water, just hangs on to water better. This is a peculiar experiment. I just wanted to see if I could get milk to curdle. So I threw in some milk, some liqueur, some water, some iodine, some digestive enzymes, just let it heat. And sped up 64 times. You can see that the unstructured sample here curdled much more quickly and completely. Which brings us to the whole notion of shelf life and spoilage, which I'll talk about. These were mustard seeds deliberately grown in an inhospitable environment. I packed cotton as tightly as I could into these glasses so they would be poorly ventilated. And these still grew. This smelled so awful, I almost fainted. I literally almost knocked myself out smelling this. And these still grew. They had a little smell, but it was almost odorless. Here are some daffodils, I think. And this almost knocked me out. This was putrid. I never knew flowers could stink that bad. I never let flowers go that long, and my goodness, awful, and this was nearly odorless. So there's something about the effect of this structuring process on plants. I just put them in structured water. Cut flowers, just put in structured water. And so here comes the really intriguing portion here, diesel fuel optical engine testing. We structured diesel fuel. And when you ask how the structuring is done, it's done, well, I can show you what I did to structure the diesel. This was a study funded by the UK government. I told them that I had some effect on fuels, and they said, well, what the heck, we'll try it. So this is the charger. Now, how I charge these up is a trade secret, but these are just chargers. They're not magnets, they're not batteries, you can't hook electrodes up to them and measure a voltage difference. They're just what they are. And this sits next to a can of 5 liters of diesel. After 2 to 5 minutes, it's almost odorless. Well, right away the smell is altered. So we then had a university burn this diesel in an optical engine at different injection timing points. So the first 3 videos just show the control and then 2 differently structured samples. So I had a slight variation on this theme, and this is normal combustion. The fuel is injected, the light goes off, and as you would expect, that's what normal combustion looks like at 10,000 frames per second in an optical test engine. We then tried to get this engine to burn structured diesel. So fuel is injected, light goes off, waiting patiently. Where is the combustion? Just a smidgen, so it's severely delayed, which is obviously not great for the environment. The good news is you don't have to inject fuel at 10 centimeters. That's just the way this test was designed. And by the way, fuel is now so well characterized. They now have formal models, so they can run experiments with virtual fuel and know how it's going to burn in different engine configurations. Not with this fuel. It breaks those models. So this is just a slight variation on the same theme. Injected, light goes off, almost no combustion. These tests were conducted over several weeks by a fourth party. The university that was supposed to do this broke their engine. They sent it to another university, and they had no knowledge of which was what sample. They just assumed they were different varieties of diesel. So we then advanced the injection timing, meaning we inject the fuel much earlier at 20 centimeters, so twice the distance to the end of the cylinder cycle. As expected, standard diesel burns probably less than optimally, but it burns. This was the O sample. Fuel is injected, light goes off. You wait what feels like an eternity. It should have already burned by now. And you think, oh, come on, any day now. And you get a completely different combustion. The The B sample is even more striking. So once again, fuel is injected, light goes off, which at that point you would expect it to burn, and you wait. And a much different dynamic there. No hot spots, the whole thing just seems to go at once. So we then sent this for post-chemical analysis. We sent samples off to an independent laboratory. And thankfully there was no transmutation, no strangeness. It all looked chemically the same, except for two important differences. One, the cold, what they call the cold filter plugging point, or the point at which the fuel actually freezes and will not go through the injectors. This is normal. This is -18. That's the normal so-called freezing point of the fuel in the injectors. And the ignition delay is 4.08 milliseconds. Well, structured diesel freezes at -15 degrees centigrade. 3 degrees centigrade is a lot, I'm told, in the fuel business. And the delay in the combustion was 4.12 milliseconds. So this was just an emulsion I did very recently. I shook water with peanut oil, salt water with peanut oil, with little Brillo pads and embedded with the soap, and just shook them simultaneously. I even switched hands to make sure I wasn't shaking differently with your hand. And you see this this film on the right. It just adhered to the glass. Just sort of an experiment with making an emulsion. And this is, I think, the last test. This is, I think, 1 frame per minute time-lapse film. This is gin with peanut oil. And as you can see, over a period of maybe 3 hours, this separates. And then the next video just shows me swirling. And you can see there's a cone, if you will, but the boundary layer is much thinner on the structured sample than on the right. On the right, it's actually, it's obvious. It's much more round. So that is it, except for an ice melt test. I must show you this quickly. Structured water gives off a little bit more. It sublimates a little bit more while freezing, and then after significant melt has occurred and the water is poured off of both samples, the structured ice obviously melts faster. So it's always a faster melt for this. So that's that.
Okay, thank you very much. No time for questions, but I really appreciate Mr. Winey because I know what we'll do at dinner time. We'll ask him to structure our wine here.